Okay, so what we're going to do today is solve exponential equations using logarithms. So, in the past we've been looking at polynomial equations and we solved them. So we found x values to make the statement true. We did it again last unit with rational expressions, finding the x values to make the statement true. So we're going to do the same thing with exponential equations. But first I want to remember this equation. So 2x equals 8. So how do I find the x value to make the statement true? Well, of course, we used a common base. And so we changed 8 into 2 cubed. And once we had a common base of 2, we could ignore the bases and just look at the exponents and say, therefore, x equals 3. Remember, I like that therefore thing because we're ignoring the bases, and the only way this statement can be true is if the exponents are equal, and so therefore, x equals 3. And we're really excited because we know how to do that, so we're going to put this. Okay, and I expect lots of yippies and cheering as you watch this video. So that's great. So we know how to solve exponential equations. So it should work all the time. So now I'm going to ask you about this. What about this? 2 to the power of x equals 5. So our yippies have turned into oh no's. And of course, if you look at it, the problem with this is finding a common base would be a challenge. So in grade 11, when we did questions like this, we kind of sheltered you from these questions. We always made it so that you could find a common base. So the numbers were nice, like 8 and 16, or maybe 27, and you found a common base of 3, or 9 and a common base of 3, or 25 and a common base of 5, Those were all the ones that we did. Well, we know that, of course, there's going to be situations where you have to find other numbers. So what happens when we don't have a common base? Well, this is where logarithms are going to come in, and hence the title, Solving Exponential Equations Using Logarithms. So how do we do this? Well, it turns out the first step is we're going to take the common log of both sides. By taking the log of both sides, we can use the laws of logarithms that we learned yesterday. And so now what we're going to do is use I think it's the power law that says if I have taken the log of some exponent, that exponent can come out front. And so that x can come out front here and say like this. So what this does is it gains us access to the x. Last year when we did this common base strategy, by having the same base, it got us access to these exponents, and we could go therefore and then investigate the exponents. When we don't have a common base, we need a different way to gain access to it. So since that x is up in the exponent here, it's a bit of a challenge. So by taking the log of it, we can use the rule to bring the x out front. And now it gains us access to the x. Now it's x times log 2. If I want x by itself, I'm going to divide both sides by log 2, the opposite operation. So I'm going to divide this by log 2 and this by log 2. Now I probably wouldn't write this out each time. I'd just do the division. And so we would have x being left by itself, log 5 over log 2. And that is the exact answer to our question. We've been able to solve it. This is called the exact answer. Okay, it's sort of like root 3 would be an exact answer. Or you could actually take the square root and get a decimal. Same thing here. We have log 5 over log 2 is the exact answer. So it would be precise. But you could punch this in your calculator since we're taking the common log. This is the one that our calculator can do. So we type in log 5 or 5 log, however it works on your calculator, divide by log 2. And you get x to be about 2.3219. I know it can go further than that, but we're going to go, when I want the actual decimal, I want you to go as far as 4 decimal places. Accuracy is key here. Okay, 4.3 is not good enough. So what does it mean we've done? Well, we've actually found the x value right up here that gets us a 5. So you can check. We're not going to check each time, but if you go and go 2 to the exponent 2.3219 on your calculator, you should get pretty close to a 5. Of course, if you were able to put all the decimals in there or the exact number, you'd get exactly 5, but we should get pretty close. And you can check there, if you put 2 to the power of 2.3 or to the exponent 2.3, not accurate enough, not close enough to 5. So that's why we're going to 4 decimal places. Okay, so this is our strategy. We'll come in this. It's take the log of both sides. Sometimes I'll ask for the exact answer, and sometimes I'll ask for the 4 decimal answer. All right, so let's see it happen again in the second one. So here we are again. If we take a quick look at this, 3 to the x plus 2 equals 4. Common log will be very challenging. We don't have a common log. So we're going to have to use logarithms to solve this exponential equation. All right, so step 1, take the log of both sides. By taking the log of both sides, it gains us access to this exponent because we have the power law of logarithms. When you're taking the log of a base with an exponent, that exponent can come out front. And this time, instead of just like a regular old exponent like the last one where it's just an x, this happens to be an x plus 2 exponent. But that's okay, that whole thing comes out as x plus 2. I'm putting it in brackets so we make sure the whole thing is being multiplied by log 3, not just the 2. If you didn't have the 2 there, that might not be obvious. Okay, so now we can solve for x. We see that x plus 2 here is being multiplied by log 3, so I'll divide both sides by log 3. We're going to get x plus 2 equals log 4 divided by log 3. And now we just have one more step to get x by itself. We have a plus 2, so we're going to have to subtract 2 from both sides. Minus 2. That, of course, would be the exact answer. If you really wanted the 4 decimal ones, you can punch it in your calculator and check that it's negative 0.7381. Okay, so same steps as before. Take the log of both sides and isolate for x.